The third lecture on quantum mechanics, Schrodinger equation. In the earlier class, we have discussed that rho is equal to psi star psi is the position probability density. That is, psi star psi dV is the probability of finding the particle within a small volume dV around r at time t, and J is the probability current density, which is a measure of particle flux, that the how many particles crossing per unit area at r and at time t is a measure of is governed by J, the probability current density. And we have also seen that for plane wave and for spherical and cylindrical wave, that is for known waveforms, the probability current density corroborates with our concept, with our existing concept. Today we shall consider what should be the condition that is satisfied by psi of x. That is the wave function. What is the condition to be satisfied by this? Actually, we obtain psi, the wave function, by solving differential equation, and the solution of the differential equation will involve the constant of integration. So to find out the constant of integration, we need to know some condition that should be imposed to us, that will enable us to find out the constants of integration. Firstly, since psi star psi is the probability density and every other information is obtained from psi as permitted by uncertainty principle. So at a point, if you want to know anything unambiguously, then the one condition is that the wave function must be finite and single valued. Secondly, psi star psi represents a probability density. That is, if a particle say moves along this trajectory and then makes a jump to come over there and then moves along this trajectory. Obviously, it is a quantum trajectory, so we will have a width, and so if we look from this side, the particle moves. What is the probability of getting the particle over here? It is given by the rho at this point, and the probability of finding the particle over here is given by the rho at the second point. In between, the particle moves as a particle from 1.1 to 2. The transition from 1 to 2, the particle makes as particle, because in non-relativistic theory there is no question of annihilation or particle creation. So the particle remains particle. Only thing that may happen, that here the probability is less, that is the particle is less probable to be there and more probable at some other place. That is to say that the position probability rho should vary continuously from point 1 to 2. Not only this, all to the right of trajectory 2 and to the left of the trajectory 1. That is to say, psi star psi has to be continuous. So this condition is that psi is continuous. Secondly, one thing, that if we differentiate psi with respect to position, I get the position eigenvalue, momentum eigenvalue, that is minus I h cross nabla. This is nabla operating on psi, gives you the momentum times psi. So momentum is obtained from the special derivatives of the wave function. In that case, if the momentum of the particle is continuous, then the first derivative has to be continuous also. If the particle is acted upon by some impulsive force, then the momentum undergoes a finite change, or there is a discontinuity in momentum. Then the psi may not be psi, first derivative of by psi should not be continuous. So we write that if there is no impulsive force acts on the particle, then del psi del x, that is the special derivatives etc., are continuous. Otherwise not. This under the action of impulsive forces, momentum undergoes a finite change. Undergoes a finite discontinuity. And in that case, obviously, del psi del x, leading to the conclusion that del psi del x etc. are discontinuous at the point where the impulsive force acts. Second, another important property is that if we have a particle which moves which remains confined within a finite region, say for example consider an atomic electron. The atomic electron remains confined within the atom. So for this atom, if we consider this is the nucleus and this is the electron, and x denotes the separation between them, then the wave function psi of xt as x tends to infinity must go to 0. Such states are called bound state. So we write for A for bound states. For bound state problem, psi goes to 0. Psi goes to 0 asymptotically. Note the word bound state. This is not the situation. As for example, if we consider the particle scattering, a particle 1 was coming from very large distance, another particle 2, and they come in vicinity of each other, and there some interaction takes place, and the particle moves in this direction. This is before scattering, and this is after scattering. When they were far away before scattering, there were no interaction between these two particles. So this particle 1 may be represented by a plane wave, and so particle 2. Such situation, this is not the situation when the particle 1 and 2 are interact via Coulomb potential. Coulomb potential being a long range potential, the interaction is felt even when they are at infinity. However, for non-Coulomb potential, both the particle 1 and 2 in asymptotic region could be represented by plane wave. The plane wave solution is e to the power I k x type solution, which remains sinusoidal, and in scattering case it is found that this amplitude decreases with distance. But in such cases, the wave function does not satisfy this condition. Still, the normalization condition is satisfied, and we say that for scattering case, wave function is finite as even in asymptotic region. Asymptotic region, but the condition both this category, but both the category A, the one condition is satisfied for both A and B, both A and B cases, that is the case A and B. The normalization condition prevails, psi star psi dx is equal to 1. This is called square integrability. That is the square integrable. That means psi star psi, which is called the square of psi, and the square integrable. So instead of saying both these two conditions separately, we may say that the wave function must be square integrable. That is, it can be normalized. With this concept about the wave function, let me apply this condition to some few simple cases and see what we get and how the result matches with our classical concept. So we first use the Schrodinger picture to a free particle moving in one dimension first. My first problem is 1D free particle, 1D free particle. So the particle moves in between plus infinity to minus infinity. The time independent Schrodinger equation for this problem is minus h line square by twice m. Since the time part is not there, we write it total derivative, and this is equal to E phi, or we write we consider first case 1. E is negative. Although it is physically saying this is not possible, because the free particle is one which has zero potential energy. So total energy E is the kinetic energy, which can never be negative. Still, we assume this and see where we will end up. In that case, the solution is phi double prime. I am writing double prime for the double derivative, and in this case we write E to be more minus mod of E, and the equation becomes create confusion with where alpha square is twice m mod E by h line square and is essentially a positive quantity. The solution of this equation is a e to the power plus alpha x plus b e to the power minus alpha x. If we draw the wave functions, it is found that let me draw this part first and then come to the other. This is phi axis, this is x axis, this is 0. This wave function is value is a over here, and it goes to, this is a e to the power alpha x. Note alpha is a real quantity. This part on the negative side of x, it decays exponentially from this value. So again this is the value, and if we plot this one, in the right hand side it falls exponentially, and in this region it grows exponentially. This is b e to the power minus alpha x function. If you want to find out the probability density, position probability density, which is obtained from this, and since these functions are real, we get size rho of x as and plus a cost term. It shows that the probability due to this part increases on the positive side and increases with increasing direction. On the other hand, on the negative x-axis it decreases exponentially. But for a free particle, one should have equal probability all alone. So neither this solution nor this solution satisfies the condition, the criteria of a free particle. So we conclude it's not possible. It is not possible for a free particle. This is not possible for a free particle. So we come to the case 2, that is E is positive. When E is positive, we derive this equation as where k square is twice m e upon h line square. The solution is oscillatory. The solution, so we can write solution as a e to the power I kx plus b e to the power minus I kx, or we could write it c sin kx plus d cos kx. This is known as travelling wave solution. And this is known as stationary wave solution. The present case that we have considered is this problem like this. The particle is, a free particle is moving in between plus minus infinity. So there is no boundary either on the right or on the left. So there is no question of getting reflected wave. Only thing that can happen, we do not know beforehand in which direction the particle is moving. It may be moving to the right or may be moving to the left. So this is a suitable solution for this case. This represents a travelling wave moving towards the right, and the other one represents a travelling wave moving to the left. This represents a travelling wave moving towards the right, and this represents a travelling wave moving to the left. On the other hand, this situation would be very suitable when the free particle is confined within a limited range, so the wave moves towards the right, gets reflected from the wall, and then there will be superposition of two equal identical wave traveling in the opposite direction, and stationary waves are produced. That is, when the particle is confined within a region, say plus minus a, then this solution would be very helpful. Now, so we this is the solution for the present case, the traveling a wave, a particle, free particle moving in x direction. It is not confined particle, it moves all along. So we don't have any boundary condition to be imposed on phi. Only thing is that phi has to be finite everywhere. Phi has to be single valued. Here there are two values. If we apply momentum operator on this, this part will give you the momentum eigenvalue plus p, that is the particle moving towards the right, and when it operates on this, you will have where the momentum eigenvalue will be negative, that is the particle moving towards the left. So the in the case of free particle, if we say the energy is E, then for corresponding to E we will have two values, the plus minus p, such that p square is twice me upon h line square. So for a given energy, there are two possible motion, one each with energy E and wave vector k. Sorry, it is k square. So k square, and this is if you integrate p is h cross k. So for a given value of E, we will have two p values, same magnitude but in opposite direction. That is, we say that the wave function is degenerate. That is, for a given value of E, we will have two solutions. One is we say phi plus, this is a e to the power plus I k x, and this is phi minus with b e to the power minus I k x. For this, the momentum is plus p, and for this momentum is minus p. That is, it represents a particle moving towards the right, it represents a particle moving towards the left. That much we know. We don't know anything else. The wave function is finite everywhere, and it is square integrable. Special techniques is required to integrate such systems. Either one need to use box normalization, or one need to use delta function normalization. Let me first explain this part. The probability density, if we calculate probability density for this system, rho is equal to psi star psi, and this becomes, if we take the, let me start once more. We know that the solution, we know two solutions. One is the plus solution, another one is the minus solution. The solution is this: psi of x is equal to a e to the power I k x plus b e to the power minus I k x. If we want to calculate rho of x is equal to this is phi star, and then this is from phi. If we multiply this with this, it is a modulus square. If we multiply this with this is b modulus square. And if we multiply this one with this, it is a star b e to the power minus twice I k x and if we multiply this with this, it is b star a e to the power twice I k x. If we assume AB to be real, if AB real, then it is a square plus b square plus it is AB this term when A, B are real numbers, this part. This is cos plus this is called the interference term. This is the probability of the forward wave or the wave traveling towards the right. This is the probability of getting the probability of the wave traveling towards the left. And this is the interference term, that is the term that arises due to the superposition of right moving and left moving term. This is the interference term. Whatever may be the case, if we want to integrate it over plus minus infinity, since A and B are non-zero quantities, the integrand diverges. It may seem that the normalization condition is not satisfied. Then there are two techniques generally applied. One is called box normalization. Consider the motion of an electron, free electron, in a crystal lattice. Then the crystal lattice is if we assume that the lattice, the physical dimension of the lattice is much longer than the separation between its two consecutive atoms within the lattice, then we may think of that the electron moves in a periodic potential, and the period is the special period is the separation between two atoms in the crystal, and the entire crystal apart from its ends can be constructed by repeating the basic block. In that case, if lambda be the special period, then we integrate it from 0 to lambda or in the interval of lambda, and we see that the entire thing can be constructed by repeating this basic block. This leads to the box normalization. Another normalization condition can be obtained from the property of Fourier transform. We know that delta k minus k prime is of the order of e to the power I x k minus k prime dx integration over x. If we take this part and we say that there are two waves having slightly different k, so we say one is k, this is e to the power I k x, this is the wave with wave vector k, and we have another wave with wave vector k prime, so it is I k prime x. Now we say that what is this condition? This is of the form e to the power I x k minus k prime dx, and this is of the order of delta, and this is nothing but delta k k prime. Such technique are used in scattering theory and is known as delta function normalization. Another one that was used in periodic lattice is called the box normalization. This is all about free particle, unbounded free particle. Now let me come to the particle when it is confined within a limited range. Again, we are considering a free particle, but the particle is confined between, say, 0 to a. So to say, the particle cannot go on the left of 0 and on the right of a. This is called a free particle, a particle in a box, 1D box. And since the box is a rectangular shape, it is called the particle in a 1D rectangular box. Here we will have, oh, the one thing that I forgot, that since there is no condition imposed on k, so any k value is allowed. Since any k is allowed, any E is allowed. E is equal to h lime square k square by twice n. So there is no quantization at all. So the energy spectrum for an unbounded free particle is a continuous energy spectrum. Now we come to the case 1D box. The situation is like this. Say this is the potential. We have a free particle which is free to move between 0 to A. If one goes here in this region, the potential is constant, we assume it to be 0. In this region, potential is infinite. In this region, potential is infinite. So these two regions, in these two regions, the kinetic energy is negative. So these two are for here the particle we cannot have particles. So we say the wave function is 0 in this region and it is so in this region. There is an interface between this region and this region which is at x is equal to 0. So when we need to apply boundary condition over here. Another interface is at x is equal to A, and here these two regions meet. So there is another point where the boundary condition has to be applied. Now, since the potential changes by infinite amount, the force that is experienced by the particle at the walls of the well are impulsive force. So for example, the particle moving towards left gets reflected back from this, and here the force that acts on the particle is an impulsive force, because changing x by very small amount, the potential changes by an infinite amount, which results in an infinite force, that is the impulsive force. And similar thing happens over here. So we cannot apply the continuity condition of the first derivative of the wave function, because the subsystem is being acted upon by impulsive force. So the first derivative of the wave function is not continuous. So the boundary condition should be, since the wave function is 0 in this region, and it should match with the wave function in this region, that is within the well, at x is equal to 0. So the x is equal to 0, the wave function must be 0, and so is at x is equal to A. That is to say, this is the wall of the well, the wave function is 0 all alone and 0 all alone, and in between the wave function can approach 0 in any direction, from positive side or from negative side. So the wave function may be like this, the wave function may be like this also. But the basic condition is that the wave function has to be 0 at the two boundaries of the well, and no continuity of no continuity of phi prime as impulsive forces on phi prime at the boundaries as there are impulsive force, there are impulsive force. So with this much, you write the boundary condition, Schrodinger equation. So time independent Schrodinger equation for region x less than equal to a greater than equal to 0 is minus h line square by twice m and E is positive. We know we have learned from the earlier discussion that E, for a free particle, E cannot be negative, so we conclude that phi double prime plus k square phi is equal to 0, where k square is twice m E upon h line square and is a positive quantity. Again, the solution may be in the form of traveling wave or in the form of stationary waves. But here the situation is something else. The particle moving towards the right gets reflected from the right wall and starts moving on the left. So there is a possibility that the stationary waves is generated within the well. Keeping this in mind, we opt for the solution like this: A sin kx plus B cos kx. This is the solution. Note the difference. For a free particle, unbound free particle, we choose the solution in the form of traveling wave. Since here there is a possibility of forming stationary wave, we have opted the sinusoidal solution in the form of stationary wave. If we apply the boundary condition, this is equal to 0, we get this part 0 plus B, which immediately denotes that B is equal to 0. So this part is no more there. The wave function now reduces to simply the sine part. So the wave function now becomes sine phi of x is equal to A sine kx. Boundary condition: x is equal to A is equal to 0 is equal to A sine ka is equal to 0. The one possibility is this equal to 0. This leads to a trivial solution, and this leads to 0, leads to quantization. Let me explore this. This is equal to 0, so this is equal to sine Ka is equal to 0. This is sine of n pi. That means the k cannot have any value. K can have only few discrete values and given by n pi by a. So with n is equal to 1, 2, etc. natural number, n is equal to 0 gives a trivial solution. So now the allowed values of k are pi by a, 2 pi by a, and so on and so forth. So writing this, it is pi by a, 2 pi by a, 3 pi by a, nothing in between. Since k is quantized, energy is given in terms of k square, so energy is also quantized. Now E now comes to be quantized. En is equal to, note that k square h line square kn square, because k is now quantized by 2n, and we write it as pi square h line square twice m a square n square. We write it as epsilon n square, where epsilon is the unit of quantization, pi square h line square by twice m a square. The numerator involves fundamental constants. Only in the denominator there are two quantities which are variable. One is the mass, which is the characteristics of the particle subjected to the well, and A, the width of the well. So there is a combination of the particle characteristic and the well characteristic. If so this is the quantization unit. We see that the energy is quantized and the quantization unit is epsilon, and it is quantized so that the minimum possible energy is E1 is equal to epsilon. Then the next energy is E2 is equal to 4 epsilon. Then E3 is equal to 9 epsilon. So if we write the energy spectrum, it is the zero energy. The first is epsilon, then 4 epsilon, then 9 epsilon, and nothing in between. N is equal to 1, 2, 3. No energy is allowed in between. The particle can have energy either epsilon or 4 epsilon, nothing in between. If some energy is being supplied from externally, if the energy matches, that the particle may jump from here to here, then it absorbs this energy. If it is not sufficient, say the energy is in excess of something, that the energy levels was there, so the particle does not make any transition. This is in some sense is the Bohr's theory, the stationary orbits, and if the particle is given a right amount of energy, then a transition is possible from one level to another level. If the energy doesn't match exactly, there is no transition. Another thing that I want to make, what is the effect of quantization rule? If you consider a particle, a macroscopic particle, say particle of mass 1 gram, subjected within a well of 1 centimeter, we will find epsilon to be of the order of 10 to the power minus 40 or even less in electron volt, in the units of electron volt, which we cannot measure by the present day available instruments. In other case, we can have an electron subjected to a well of the order of angstrom. Then we find that epsilon is of the order of few electron volts. So there are four combinations: macroscopic M or microscopic M, and macroscopic A and microscopic A. The three combinations involves either macroscopic M or macroscopic A. In such cases, epsilon is found to be very small, to be detected experimentally, and only when M and A both are microscopic, the epsilon becomes sizable and the quantum effect is felt. Furthermore, if we draw the wave function, the n is equal to 1. Let me first normalize the wave function. Then the wave function now depends on n, and so the wave function becomes phi n of x is equal to a n sine k n x is equal to a n sine n pi ax. So normalization condition is 1 integration phi n star phi n dx from minus infinity to plus infinity, that is all space. We break this integration into 3 parts. This region is 0 because the wave function is 0 in this region. This is 0 as the wave function is 0 in the region. So it remains only this part. So this basically becomes 0 to a phi n star phi n dx is equal to 1. And if we write it, it is a n modulus square integration sine square n pi ax dx from 0 to a. Using the standard result, it becomes a n square into a by 2, so that we lead to the conclusion that a n modulus is equal to root 2a, and the normalized wave function for this free particle is x is equal to 0, the wave function is 0. If x is equal to a, the wave function, this is sine n pi, again 0. In between, there is no zeros of the wave function. So the plot of the wave function will be like this. This is the well. This is n is equal to 1. For n is equal to 2, For n is equal to 2, the wave function is 0 at x is equal to a and at x is equal to 0. Furthermore, it is also 0 at x is equal to a by 2. X is equal to a, n is equal to 2, so the result becomes 2 pi by a. This is n and this is a by 2, so this is again pi. So the wave function for n is equal to 2 state will be, this is n is equal to 2, and for n is equal to 3 we will have wave function 0 at a and at two other points, which equally divides this in 3 parts. So the wave function will be, and so in general, if the quantum number is n, there will be n minus 1 nodes. I am in counting nodes, the extremities are not considered. So n is equal to 1 state has no nodes, n is equal to 2 state has 1 node, and n is equal to 3 state has 2 nodes. So phi n has n minus 1 nodes. Something funny, it is something funny that if we consider this the corresponding probability densities, it is the plot of phi n, and if we plot the corresponding rho n, for this it is n is equal to 1, for n is equal to 2, and for n is equal to 3 we have the probability plot like this. Now we consider that this says that it is most probable for n is equal to 2. It says that it is most probable to find the particle at a by 4 and 3a by 4, and it is 0. Probability is 0 of having the particle at a by 2. It may look strange how the particle could be more probable to be on these two peaks. And how can the particle can move from here to there without passing through this midpoint. This is strange when we think of the particle in terms of particle aspect. But for a wave, we know that such phenomena is all possible. That is to say, in microscopic world, the particle exhibit wave nature, and from wave character consideration, this is possible effect. This much for the application of boundary condition. In the next class, we shall continue with the further properties of the wave function. Till now, we have considered two interpretation for the wave function. One is the probabilistic interpretation of Born. Secondly, we have discussed the probability current density, and now we have applied the boundary condition, what are the boundary conditions to be satisfied by the wave function, and we have considered two examples where we have applied the boundary conditions. In the next class, I shall consider another example where I shall use the concept of probability current density and try to convince ourselves that the introduction of probability current density is indeed helpful in calculating the particle flux in the asymptotic region.